So we are now on the third part of Chapter 5, Stresses in Beams. So didiscuss natin dito yung analysis of flexure action. So I have here a figure that shows the bending of a layered beam. So this beam is composed of many layers, and assume that it has no adhesive between each layers. So the separate layers would slide past each other, and the total bending strength of this beam would be equal to the summation of the strength of each layer. So the horizontal layers in a solid beam are prevented from sliding by shear stresses that act between the layers. That's why built-up beams are weaker compared to the solid beams. So let us try to analyze this figure of a beam. So the shaded portion of the beam requires a longitudinal force that is equal to F, and our P is the resultant of the normal stress acting on the area. So ito yung ating beam, and the cross-sectional area would look like this. So the longitudinal shear force F is equal to the resultant of the normal stress acting on our area. So in the shaded portion of A, kuha tayo ng small portion na tatawagin nating differential A, or an element dA, in which yung stress would also be equal to the differential P all over the differential area, which the stress is also equal to our negative value of moment multiplied by Y all over I. So equating these two equations, we have the differential P all over the differential A is equal to negative M Y all over I. And then transposing dA, so we have integrating this over the area, we have P is equal to Y dA, in which yung ating Y multiplied with the differential area would be equal to our Q, or our static moment of area. That's why we have P is equal to negative M multiplied by the static moment of area all over the moment of inertia. This would now be the resultant force acting on the phase 1 of the body. So P is equal to negative moment multiplied by the static moment of area all over the moment of inertia that is acting on the phase 1 of the body. Next, let us consider another phase in the beam. So meron na tayong phase 2 kanina. We are just considering phase 1. So the bending moment acting at section 2 is equal to M plus the differential moment, and it is the infinitesimal change in M over the distance dx. Therefore, the resultant normal force acting on phase 2 will now be equal to this 1. So, di ba meron tayong P is equal to negative M multiplied by Q all over I. So, considering the normal force acting on phase 2, so we have P plus the differential P minus P is equal to negative. Sa moment naman tayo, so we have M plus dM multiplied by Q all over I. And then at the left portion, so we have negative value of negative M of Q all over I. So we have negative M Q all over I plus dM of Q all over I plus M of Q all over I. So cancel this out. So, meron tayong let's consider this as our equation number 1. We know that equilibrium can exist only if there is an equal force or an equal and opposite shear force acting on the horizontal surface. So let shear would be the average shear stress acting on the horizontal surface. Therefore, the resultant would now be equal to differential F is equal to the shear force multiplied by B multiplied by dx. Therefore, taking the summation of forces horizontal is equal to 0. So we have P plus dt minus P plus the shear force multiplied by B dx is equal to 0, in which P plus dt minus P is equal to the differential M multiplied with Q all over I, plus shear of B dx is equal to 0. We have a correction here. So this is supposed to be negative dm q all over I. So this must be negative. So take note, meron tayong correction dito. Negative. So this is negative. Negative. So ayusin lang natin. So transpose natin at the other side yung part na to. Diretso ko na lang. So we have shear is equal to the value of dm all over dx multiplied by q divided by I d. So, transpose ko lang and then sinet aside ko yung ating shear force, in which the derivative of m all over dx is equal to our shear, right? From the relationship between the shear force and the bending moment. That's why we now obtain the average horizontal shear stress is equal to V, or our shear force, multiplied by the static moment of area, Q, divided by the moment of inertia multiplied by B, or the width of the beam, or the width of the cross section. So this is now the average horizontal shear stress that is acting on the beam. So we have here a small portion of our beam. So, i-drawing lang natin yung stresses niya. So, let us draw the stresses. So, the stress diagram will look like this. So, we have here dy and dx. And then, we have a vertical shear stress. So, let's say this is vertical shear stress. So, ito yung vertical and this is the horizontal. So, another one we have here, horizontal shear stress. And then another vertical shear stress and a horizontal shear stress. So, this is the stress diagram. So, let us proceed to the force diagram, in which yung ating force, diba, is equal to stress multiplied by the area. So, we have the stress is equal to vertical shear stress. Yung area niya is dz multiplied by dy, or dy multiplied with dz. And then on this part, we have the horizontal shear stress multiplied with the area. So ano yung area? Dz multiplied with dx, or dx multiplied with dz. And on this part, we have a vertical force on which it is equal to vertical stress multiplied with the area, which is equal to dy dz also, dy dz. And then on this part, we have here the horizontal shear stress multiplied with dx multiplied with dz, dx multiplied with dz. Let us put point A here. So by taking the summation of moment at A is equal to 0. So we have shear stress vertical multiplied by dy dz. So moment arm is, so the moment arm would be equal to dx, tama? And then we have also minus the horizontal shear stress multiplied with dx dz And then moment arm is dy. Is equal to 0. Common term, they have dx, dy, and dz multiplied with the vertical shear stress minus horizontal shear stress is equal to 0. So cancel this one. Therefore, it will yield that our vertical shear stress is equal to our horizontal shear stress. So we can now conclude that the shearing stress acting on one face of an element is always accompanied by a numerically equal shearing stress acting on a perpendicular face. So for the application of shearing stress to rectangular section, let us try to derive a special formula for rectangular section. So for example, we have here a rectangular cross-section of a beam. So this is the neutral axis. And meron tayong shaded portion, our specific area. So we have here B that is located at a distance y from the neutral axis. And this is h over 2. Kasi ito yung ating h. So our shearing stress is equal to VQ all over IB, in which yung ating Q is equal to the area of the shaded portion multiplied by the distance from the neutral axis to its centroid. So let's say this is y bar. So we have, so lagay ko dito. So VQ all over IB is equal to, so yung Q natin is equal to B multiplied by H all over 2 minus Y. So ito yon, B multiplied by H over 2 minus Y. And then yung kanyang distance from the neutral axis to the centroid is equal to Y plus H all over 2 minus Y all over 2. Let us simplify it further. So, lipat ko na lang dito. So, we have here B all over I. So, pwede ko nang i-cancel out yung B. Tama. So, we have B all over I multiplied by H all over 2 minus Y. All over 2 and then all over 2. So, simplify natin to. Kasi medyo complicated. So, it would be equal to h minus 2y all over 4. So, we have b all over I. So, labas ko yung 1/2. So, meron tayong b all over 2i. So, we have v all over 2i multiplied by h squared all over 4 minus y squared. Minus y squared. So this formula shows that the shearing stress is distributed parabolically across the depth of the section. So the shearing stress is distributed like this. So it is distributed parabolically. So the shearing stress is distributed parabolically all over the area of our beam. Now, the maximum shearing stress occurs at the neutral axis and is found by substituting the dimensions of the rectangle. We have so the maximum shearing stress now will occur at the neutral axis. So let us say this is the rectangle. This is the neutral axis. So let us consider this full area. And this B and this is H all over 2. So yung ating shear stress is equal to V, and then the moment of inertia for rectangle is 1 all over 12 of BH cube multiplied by B, and then the Q, the static moment of area, is equal to B multiplied by H all over 2, and then H all over 2 divided by 2 is equal to H all over 4. So we have here V of BH squared multiplied by 8 all over 12 of B squared of H cube. So we have here is equal to 12 of V BH squared all over 8 B squared H cube. So cancel this out, and then this one. So 12 divided by 8 is equal to 4. So 12 divided by 8 is equal to 3 all over 2 multiplied with V, and then we are left with BH, in which B multiplied by H is equal to the area of the rectangle. So we have now the shearing stress is equal to 3 all over 2 multiplied by the shear force divided by the area of the beam. So this is the maximum shearing stress that will occur in the rectangular section, in which it is equal to 3 all over 2 multiplied by the shear force all over the area. So we have different limitations of the shear stress formula. So the first limitation, the shear stress formula predicts that the largest shear stress in a prismatic beam occurs at the cross section that carries the largest vertical shear force. Limitation number 2, the location of the maximum shear stress within that section is determined by the ratio of static moment of area all over B. So Q is always maximum at Y is equal to 0, or the neutral axis. However, if the width at the neutral axis is larger than at the other parts of the cross-section, it is necessary to compute the shear at 2 or more values of Y before its maximum value can be determined. So when deriving the shear stress formula, shear should be considered at the average shear stress. And the shear stress formula is sufficiently accurate for rectangular cross-sections and for cross-sections that are composed of rectangles such as W and S shapes. And for other cross-sectional shapes, the formula must be applied with caution, just like the rectangular section. So we have here the procedure for analysis of shear stress. The first step is use equilibrium analysis to determine the vertical shear force acting on the cross-section containing the specified point by drawing the shear diagram. So next is to locate the neutral axis and compute the moment of inertia of the cross-sectional area about the neutral axis, especially if the moment of inertia is not given in the properties of the cross-section. The third one is to compute the first moment of the cross-sectional area that lies above or below the specified point. Next is to calculate the shear stress from this formula. The shear force multiplied by the static moment of area all over the moment of inertia multiplied by the width, where B is the width of the cross-section at the specified point. So take note that the maximum shear stress on a given cross-section occurs where Q all over B is the largest. If the width B is constant, then maximum shear stress occurs at the neutral axis because that is where Q has its maximum value. And if B is not constant, it is necessary to compute the shear stress at more than one point in order to determine its maximum value. So for example number 1, the simply supported wood beam is fabricated by gluing together three 160 mm by 80 mm planks as shown. Calculate the maximum shear stress in the glue and in the wood. So we have here a beam that is 6 meters long. So ang cross section ng beam natin will look like this one. So ito na yung since this is a rectangular naman in shape, ito na yung ating neutral axis. So kukunin natin yung maximum shear stress in the glue. So at this part, so ito, naka-glue siya on this part, yan. Therefore, ang i-consider nating area would be this one. So meron itong centroidal or centroid. So ito na yung ating Y bar. And yung Y bar natin is equal to, so this is 80 millimeters, this is 40, this is 40, and this is 80. So yung Y bar natin would be equal to 80 millimeters plus 40 millimeters. That is referred to our neutral axis. So yung ating maximum shear dito, so kung drawing natin yung shear diagram niya, we have the reaction 1 is equal to 8 times 6, 8 multiplied by 6 multiplied by 3 divided by 6. So we have here 24 kilonewton, and also here 24 kilonewton. So yung shear diagram niya will look like this one. Yan. So this is 24 kilonewton and this is 24 kilonewton. So the shear or the maximum shear is equal to 24 kilonewton. That occurs to the support. So ito yung maximum shear niya and it occurs at the support. So next, and our maximum shear stress, diba, is equal to the maximum shear, Vmax, multiplied by the moment of the area, Q, all over the moment of inertia multiplied by B, in which yung ating Q is equal to area multiplied by Y bar. So the area is equal to 160 millimeters multiplied by 80 millimeters multiplied by our Y bar. So yung Y bar natin is equal to mali yung Y bar natin dito. So yung Y bar natin is equal to 40 millimeters ito plus 40 millimeters. So it is equal to 80 millimeters. So multiplied with 80 millimeters. Therefore, Q is equal to 160 times 80 times 80. So we have 1.024 times 10 raised to 6 cubic millimeter. And then we have yung Vmax natin is equal to 24 kilonewton. So times 10 raised to 3 newton multiplied with Q, which is 1.024 times 10 raised to 6 cubic millimeter all over I. So yung I natin is 1 all over 12 moment of inertia of B. So B is 160 millimeters. H is equal to yung overall depth, which is 80 times 3, so 240. So we have 240 millimeter raised to 3 multiplied with B, which is 160 millimeters. Therefore, the maximum shearing stress would now be equal to 24 times 10 raised to 3 times 1.024 times 10 raised to 6 all over 12 of 160 times 240 raised to 3 multiplied with 160. So, it is equal to 0.83. So, this is 0.833. So, we have Newton per cubic millimeter. So, cancel Newton. So, we have Newton per square millimeter, or 0.833, 0.8333 megapascal. So, this is the answer for the shear stress in the glue. So, this is our answer number 1. Next is we will consider, or we will take the maximum shear stress in the wood. So, drawing lang natin ulit yung cross section. So, ito yung ating cross section, and it is composed of 3 planks again. So, this is 80 millimeters, 80, and 80. So, this is the neutral axis. So, we will consider the maximum shear stress in the wood. So, since this cross section or this beam is composed of wood, i-consider na natin siya as one entity. So, ito yung i-consider nating area. Meron itong centroid that is equal to y bar from the neutral axis. So, yung y bar natin is equal to 80 plus 40 all over 2. So, it is 60 millimeters. So, yung centroid is 60 millimeters from the neutral axis to this point. So, this is 160 millimeters, in which our maximum shear stress would now be equal to VQ all over IB. So, yung Q natin is equal to AY bar, tama? In which yung area is equal to 160 multiplied by 80 plus 40. So, 120 millimeter. And then yung Y bar is 60 millimeters. Therefore, Q is equal to 160 times 120 times 60. So, we have 1.152 times 10 raised to 6 cubic millimeter. So, yung maximum shear natin kanina is 24 kilonewton. So, we have 24 times 10 raised to 3 newton. And then, yung Q natin is 1.152 times 10 raised to 6 cubic millimeter. All over yung I, moment of inertia for rectangle. So, we have 1 all over 12 of 160. Then, yung height is 240 raised to 3 multiplied with yung B natin is 160. Therefore, the maximum shear stress would now be equal to 1.152 times 10 raised to 6 all over 1 all over 12 of 160 times 240 raised to 3 times 160. So, it is equal to 0.9375 Newton per square millimeter, or 0.9375 megapascal. So, ito na yung maximum shear stress natin in the wood. So, this is our answer for the second part. And as I have introduced kanina, that for rectangular section, we have an equation for exclusively for rectangular section, which is equal to 3 halves of B all over A. So, itratry natin kung parehas ba sila ng sagot. So, we have 3 all over 2. Yung maximum shear natin is 24 times 10 raised to 3 Newton. And then, yung area natin is 160 millimeter multiplied by 240. 80 plus, yes, so 80 times 3, so 240 millimeter. So, tingnan natin kung parehas makukuha natin. So, 3 halves of 24 to 3 divided by 160 times 240. So, yan. So, tama yung sagot natin, 0.9375 Newton per square millimeter. So, yan. Parehas lang. If we will use the equation or the equation for rectangle or the general equation for determining the maximum shear. So, this is the maximum shear in the beam or in the wood, and this is the maximum shear stress in the glue. So, for example number 2, the W12 by 40 section is used as a beam. If the vertical shear acting at a certain section of the beam is 16 kilopounds, determine the following at that section: the minimum and the maximum shear stress in the web. So this is our W12 by 40, and it has a shear force of 16 kilopounds. And this is the properties of our section that we have obtained from our copy. We will ignore the small fillets and rounded corners present in this actual section. So these are the fillets and the rounded corners. So neglect natin yan, and let us treat this section as a combination of 3 rectangular shapes. So our moment of inertia here, as the table says, it is 310 inches raised to 4. So for our part A, the minimum shear stress in the web. So the minimum shear stress in the web occurs at the junction with the flange. So it is where Q all over B is smallest. So yung B natin is equal to 0.295. So the minimum shear stress in the web will act at this junction of the web and of the flange. So our shear stress is equal to VQ all over IB, in which our Q or our static moment of area is equal to A multiplied by Y bar. So ang consider nating area would be this one. So area is equal to 8.005 inches multiplied by 0.515 inches. And then Y bar, so this is the neutral axis, and this is 11.94 all over 2. So this is 5.97. So Y bar is equal to 5.97 minus 0.515 all over 2. Therefore, the static moment of area is equal to it is equal to 23.55 inches raised to 3. Therefore, the shear stress is equal to, the shear force is equal to 16 kips, or 16 times 10 raised to 3 pounds multiplied by our Q, which is 23.55 inches raised to 3, and then the moment of inertia is equal to 310 inches raised to 4, and then the B is equal to 0.295 inches. Therefore, it is equal to it is equal to 4,120 pounds per inches squared, or 4,120 psi. So this is the minimum. This is the minimum shear stress, 4,120 pounds. So this is our answer for the minimum stress. For the maximum stress, so the maximum shear stress is located at the neutral axis, where our Q all over B is the largest. We will consider this area. Therefore, for letter B, the maximum shear stress is equal to, again, VQ all over IB, in which Q is equal to, so yung Q natin na nakuha dito kanina, which is 23.55 inches cubed. So let's say Q1 for this one, and then Q2 is this one. So Q2 area multiplied by Y bar. So yung area is 0.295 multiplied by 5.97 minus 0.515, And then yung y bar is 5.97 minus 0.515 all over 2. So 0.295 multiplied by 5.97. So this is equal to 4.39 inches raised to 3. Therefore, the total static moment of area will be equal to 23.55 plus 4.39. So it is equal to 27.94 inches raised to 4. Therefore, the maximum shear stress is equal to, so yung ating shear is equal to 16 times 10 raised to 3 pounds multiplied by our Q, which is 27.94 inches raised to 4, all over moment of inertia of 310 inches raised to 4 multiplied by B, which is 0.295. So it is equal to 4,888.35 pounds per inches squared. So this is the maximum shear stress. For example number 3, the figure shows the cross-section of a beam that carries a vertical shear force of 12 kilopounds. The distance from the bottom of the section to the neutral axis is 8.9, and the moment of inertia of the cross-section area about the neutral axis is equal to 547 inches raised to 4. Determine the maximum shear stress on this cross-section. So the maximum shear stress may occur in the neutral axis, where our Q is the largest, or at the level AA, where the width of the cross-section is smaller than at the neutral axis, so at this part. So let us take first the shear stress at the neutral axis. So let's take the shear stress at the neutral axis, in which it is equal to VQ all over IB. So yung Q natin dito is equal to A all over Y bar. So yung area na i-consider is this area above the neutral axis. So we have 2 inches multiplied by 7.3, and then yung Y bar is 7.3 all over 2. So Q is equal to 53.29 inches raised to 3. Therefore, the shear stress equal to, yung shear force natin is 12 kips, or 12 times 10 raised to 3 pounds multiplied by 53.29 inches raised to 3 all over the moment of inertia, which is 547 inches raised to 4 multiplied by the width, which is equal to 2 inches. So it is equal to 584.53 pounds per inches squared. So this is the first assumption of the maximum shear stress. For the second assumption, let us consider the section which is at the bottom of the neutral axis, where the width is smaller compared to 2 inches. So let us have our, let's say, shear stress at AA. So we have VQ all over IB. So our Q is equal to 1.2 multiplied by 7.5 multiplied by the Y bar. So Y bar is 8.9. So this is 8.9 minus 7.5 all over 2. So yung Q natin is equal to 46.35 inches. So we have here the shear, which is 12 times 10 raised to 3 pounds multiplied by 46.35 inches all over. Yung I natin is 547 inches raised to 4 multiplied by our B, which is 1.2. So it is equal to 847.35 psi. 847.35 psi. So the larger between the two value is 847.35 pounds per inches squared. Therefore, the maximum shear stress is equal to 847.35 pounds per inches that is occurring at AA. So this is our answer. So for example number 1, a rectangular beam carries a distributed load of intensity W on a simply supported span of length L. Determine the critical length at which the shearing stress and the flexure stress reach their allowable values simultaneously. So we have here a beam that is simply supported. So we have here reaction 1 and reaction 2. And it is loaded by a uniformly distributed load of W. So this is the cross section of the beam. This is the B and this is the H. So let us consider W, or let us convert this uniformly distributed load into a point load. So it would be equal to, let's say, capital W na lang. So we have here capital W, and it is equal to small letter W multiplied with length. So ito yung value niya. So taking the summation of moment at R2 is equal to 0. So we have R1 multiplied with L minus capital W multiplied with L all over 2 is equal to 0. Therefore, reaction 1 is equal to, so transpose lang natin, we have W L all over 2 divided by L. So cancelling this out, R1 would be equal to capital letter W all over 2. And of course, they are equal, or it is equal to our reaction 2. So yung reaction 2 natin is also equal to W all over 2. So alam niyo naman na siguro yung itsura nung shear diagram if it is a uniformly distributed load, and it will look like this one. So ito yung W all over 2, this is W all over 2, and the zero shear will occur at L all over 2. Therefore, the maximum shear here is equal to W all over 2, and then yung maximum moment would be equal to 1/2 of W all over 2 multiplied with L all over 2. And it is equal to WL all over 8. So ito yung maximum moment niya. And take note, we have a formula for shearing stress that is applicable for rectangle. So di ba yung shearing stress for rectangle is equal to 3 all over 2 multiplied with the shear force all over A. So let us substitute the value of the shear force to the maximum shear that we have. So the shear stress would be equal to 3 all over 2, and then W all over 2 multiplied with yung area is B multiplied with H. So simplify natin, we have 3 all over 4 W B H. Transpose natin, so magiging 4/3 of shear multiplied with B multiplied with our H. And then, our flexural stress, right, is equal to Mach all over I. So, yung moment natin, maximum moment, is equal to WL all over 8. And then, we have our C. Yung our C is H all over 2. So, H all over 2 divided by I. So, yung moment of inertia natin is 1 all over 12 of BH cubed, diba? So, simplifying it further, we have canceling this out, so magiging squared. So we have WL all over 16 and then BH squared all over 12, and then we have WL all over 16 of BH squared, tama? So yung 12, 6, so cancel out, magiging 3/4, tama? So we have 3 all over 4 WL all over BH squared. So that is our stress. And take note that our W is also equal to 4/3 of the shear stress multiplied by BH. So tuloy ito na lang dito. So copy that one. So we have 3/4 WL all over BH squared. And then substitute natin yung W with 4/3 of shear stress multiplied with BH. So we have 3/4 multiplied by 4/3 of shear BH multiplied with length all over BH squared. So canceling this out, so we are left with H. So stress is equal to, so canceling also this one, we have shear stress multiplied with the length all over H. But the problem is asking for the critical length. Therefore, the length is equal to the flexural stress multiplied with height all over the shear stress. So this is now the critical length at which the shearing stress and the flexural stress will reach their allowable values simultaneously. So take note that for values larger than this critical length, flexure will govern in the design, but for shorter values, shear will govern. For example number 2, a box beam supports the loads as shown. Compute the maximum value of P that will not exceed the flexural stress of 1000 psi or a shearing stress of 100 psi. We will determine the value of reaction 1 and reaction 2. So taking the summation of moment at R2 is equal to 0. So we have R1 multiplied with 10 feet minus P multiplied with 5 plus 1000 multiplied with 5 is equal to 0. Therefore, reaction 1 is equal to, so transpose natin, so magiging 5P minus 5,000 divided by 10. So reaction 1 is equal to P all over 2 multiplied with 500, tama? And then taking the summation of forces vertical is equal to 0. So we have P all over 2 minus 500 plus R2 minus P minus 1000 is equal to 0. Therefore R2 is equal to, so transpose natin this one, we have 1500 plus P all over 2. So our reaction 2 is 1500 plus P all over 2, and then the reaction 1 is P all over 2 minus 500. So you will draw the shearing diagram. So we have here P all over 2 minus 500 and P all over 2 minus 500. So P all over 2 minus 500 minus P. So let us solve here. So P all over 2 minus 500 minus P. So we have
negative 500 minus p all over 2. Or, labas natin yung negative. So, we have 500 plus p all over 2. So, we have 500 plus p all over 2. And then, same in here. We have negative of 500 plus p all over 2. And then, plus 1,500 of p all over 2. So, add lang natin to with 1,500 plus p all over 2. So, magiging negative 1,000 yan. So, canceling this out. So, 1,000. So, we have here 1,000. And, tama, 1,000. Nag-close yung ating shear diagram. So, this is our shear diagram. Looking at the values and not the diagram itself because this is not in a scale, the maximum shear would now be equal to 500 plus p all over 2. So, let us determine the maximum moment. So, at this point, we have 0. And then, p all over 2 minus 500 multiplied with 5. So, we have 5 all over 2p minus 2,500 or 2.5p minus 2,500. So, we have here 2.5p minus 2,500. And then, minus, we have here 500 minus p all over 2. So, 500 so, multiply natin yung length with 5. 5. So, we have 2.5p minus 2,500 minus 2,500 plus 2.5p. Tama? So, distribute natin yung minus sign. Minus 500 plus 5 times 5. So, this is negative. So, canceling this out, we are left with negative 5,000. So, negative 5,000 at this part, we have plus 1,000 multiplied with 5. So, it is left with 0. So, it will look like this one. Ayan. So, this is negative 5,000. Then, 0. So, the maximum, ayan. So, the maximum moment will now be equal to 2.5p minus 2,500. And this is in pounds per, or pounds that feet. So, for the maximum value of P in the flexural stress, our flexural stress is equal to Mach all over I. So, 1,000 PSI or pounds that inches per inches squared is equal to yung moment natin, which is 2.5p minus 2,500. And take note, it is in pound foot. Kaya, i-multiply natin siya with 12. And then, yung ating C. So, yung ating C is 10 divided by 2, which is 5. So, 5 all over yung I. So, yung compute pala natin yung I. So, yung moment of inertia. So, I will get the whole value of this rectangle and then minus natin to. So, we have 1 all over 12 of 8 multiplied with 10 cube minus 1 all over 12 of yung nasa loob, which is 8 minus 1 minus 1. So, we have 6. Height is 10 minus 1 minus 1. We have 8 cube. Therefore, the moment of inertia is equal to it is equal to 410.67 inches raised to 4. So we have 410.67 inches raised to 4. Therefore, the value of P is equal to So P is equal to 3,737.8 pounds. And then for the shearing stress, our shearing stress is equal to PQ all over IB. So yung ating Q is equal to the summation of area multiplied by Y bar, tama? So we have here 8 multiplied by 1 times 4.5 plus 2 multiplied of 4 times 1, and then 4 divided by 2 is 2. So yung Q is equal to Q is equal to 52 inches raised to 3. So our shearing stress is 100 psi. So yung V natin is 500 plus 0.5p multiplied with 52 all over I is 410.67, which multiplied with B, which is 2. So P is equal to P is equal to 2,159 pounds. For example number 3, a box beam carries a distributed load of 200 pounds per foot and a concentrated load P. Determine the maximum value of P if the flexural stress must not exceed 1,200 psi and shear stress must not exceed 150 psi. So we will determine the value of the P. Let's see first the value of P. If the flexural stress must not exceed 1,200 psi and the shear stress must not exceed 150 psi. So again, the first step is to determine the maximum shear and the maximum moment. So by taking the summation of moment at R2 is equal to 0. So we have R1 multiplied by 10 minus P of 5 minus 200 multiplied by 10 multiplied with the moment arm of 5 plus 200 multiplied by 4 multiplied by 2 is equal to 0. Therefore, R1 would be equal to so transpose this, it will be equal to 8,400 tapos plus 5P divided by 10. So R1 is equal to 840 plus 0.5 of P. And then summation of forces vertical is equal to 0. So we have 840 plus 0.5P minus P minus 200 of 14 plus R2 is equal to 0. Therefore, R2 is equal to so transpose natin. So 1960 plus 0.5P. Tama. R1 is 840 plus 0.5P and then R2 is 1960 plus 0.5P. So drawing natin yung moment or yung shear and moment diagram. So we have here 840 plus 0.5P. 840 plus 0.5P. So 840 plus 0.5P minus 200 multiplied with 5. So we have 0.5P minus 160. So we have 0.5P minus 160. 0.5P minus 160 minus P is equal to So, labas ko na lang yung negative. So, we have 160 plus P all over 2. So, we have negative of 160 plus, let's say, 0.5 P na lang. Ayan. So, minus 200 multiplied with 5. So, 1,000. So, we have negative 1160 plus P all over 2. Tama? So, we have negative 1160 plus P all over 2. And then, we have plus 1960 plus 0.5 P. So, cancel this out. We are left with 1960 minus 1160. So, we are left with 800. So, 800 minus 200 times 4. Yeah, so tama. It is 800 at this part. So, we have 800 and then 0. So, this is our shear diagram. Yan. In which our Vmax is equal to negative 1160 plus P all over 2. Moment, we have a 1/2 of 840 plus 0.5 P plus 0.5 P minus 160 multiplied with the length, which is 5. So we have 2.5 and then 840 minus 160. So we have 680, 0.5, 0.5. So we have plus P. Ayan. And then we do not have moment. And then we have here area. So minus 1/2 of 160 plus 0.5 P plus 1160 plus P all over 2 or 0.5 P multiplied with 5. So we have 2.5 P, 680 plus P, this is also 2.5, and then 160 plus 1160, we have 1320. So we have 1320 plus P, tama? Therefore, it is equal to, so walang P pala yan, sorry. So walang P to. So distribute nga natin. So 2.5 times 680. So we have 1,700 plus 2.5 P minus 2.5 times 1320. We have minus 3,300 plus, or sorry, minus 2.5 P. So canceling this out, we are left with negative 1,600 plus the area of this 1/2 of this is 800, tama? We have 800 multiplied with 4. So, it's equal to 0. Therefore, the maximum moment is equal to 1,700 plus 2.5 P. Paano ko nakuha yun? So, let us plot the moment diagram. So, we have here 2.5, 0, and then we have here 2.5 of 680 plus P, tama? So, ang maximum is 1,700 plus 2.5 P. Therefore, we're now ready to solve for the value of P. So first, for the flexural stress. So for the flexural stress, we have our formula of Mach all over I. So we have Mach all over I. But first, we will determine the value of I. So yung I natin is equal to 1 all over 12 of, so this 8, 9, 10. So we have 10. And then the height is 10, 11, 12. So 12 cube minus 1 all over 12 of 8. Height is 10 cube. So I, or the moment of inertia, is equal to it is equal to 773.33. Inches raised to 4. Therefore, our moment, so lagay ko na lang dito para hindi masyadong crowded. So, our flexural stress is 1,200 psi. Moment is 1,700 plus 2.5 p. And remember that is in pounds foot. So, multiply natin siya by 12. Tama? So, by 12. And then, yung ating C is, so we have 12 divided by 2, we have 6. And then, ang ating I is 773.33 inches raised to 4. Therefore, P is equal to is 4,475.54 pounds, and that is under flexural stress. So for our shear stress is equal to VQ all over IB. So determine natin yung value ng Q. Yung nasa labas we have 8, 9, 10 multiplied with, so 5, 6, so we have 6, and then 3 minus yung nasa loob, which is 8 multiplied with 5 multiplied with 2.5. So it is equal to it is equal to 80 inches raised to 3. So yung ating shear stress is equal to 150 psi. Our maximum shear is 1160 plus P all over 2. Then yung Q natin is 80. Moment of inertia is 773.33, and then yung ating B is 2. So the value of P now is equal to it is equal to 3,479.98 pounds. So comparing the value of these 2P, so we have 3479 and 4475. Therefore, we will consider the smaller one as the safest value that the beam will carry as our point load. So our final answer is 3,479.98 pounds.